Hi. What we're going to be covering today is van der Waals equation, and we're going to be deriving some of the van der Waals equation and breaking down some information about it. So to start, I wrote down the van der Waals equation here. You have P, pressure, is equal to RT, your gas constant times temperature, over V minus B minus A over V squared. Now there's a couple variables that are unknown in there, V, A, and B. V is simply the molecular volume of this, and excuse me, B is like the actual occupied volume in our system. And then A is an attraction constant. So we need to look at the curves that the van der Waals equation produces. So if you see these curves, they sort of begin to produce an inflection point at a given location, and this point of inflection can be used in order to assume that the derivative and the second derivative are set equal to 0 below this point of inflection. So we're going to take the first and second derivative of this equation. So you see this right here? Yeah, so the first derivative is simply dp over dv is set equal to negative RT over V minus B squared plus, not minus, 2A over V cubed. And breaking this down one more step, the second derivative would just be d squared p over dv is equal to positive RT over V minus B cubed plus 3A over B cubed. I think everybody can see that. To continue breaking these down in order to solve for A and B, I'm going to put everything, put these on different sides of the equation for each of the derivatives. So what we've got is 2A over B cubed is equal to RT over V minus B squared. And also 3A. I made an error before. This is not supposed to be V cubed. This is actually supposed to be V to the fourth. So this would be 3A over V to the fourth is equal to RT over B minus B to the third. Okay, just double checking these. Yes, that's correct. So now what we're going to want to do is multiply first derivative by the reciprocal of the second derivative. 2A times V to the fourth over 3A V to the third is equal to RT V minus B to the third over RT V minus B to the second. So this we can continue to break down and cancel out. So here our A's cancel, V's cancel except for one on top here. Both of our RT's will cancel. Our VB's cancel out except for one on top here. Excuse me. So this will yield us 2/3 V is equal to V minus B. Yeah, B minus B. And then we can pull B out of this equation, since we have canceled out our A's by doing this, which yields us with B is equal to, let's see, that'll be V over 3. So we've got our B set up for our critical values. Okay, so now what we're going to do is take what we have gained so far and use it to solve for A. So we're going to take this B is equal to V over 3 and plug it back into our first derivative. So that's going to give us, let's see, that'll be 2A over V cubed is equal to RT over 2/3 V squared. All right, and then for simplification moving forward, I'm just going to say this 2/3. I'm going to make this 4/9, 4 over 9. So everybody can see that. Now we can set A equal to, we can pull A out of this, and we have A is equal to, let's see, that would be 9 over 8 times RT times R volume. All right, so now we have A and B solved for our critical values. So critical, yeah, everything is set up here is set up for critical pressure, critical temperature, in order to solve in the van der Waals equation, because we need the inflection point at the critical values. So we can punch these back into our original equation, which would yield us P is equal to RT over V minus V over 3 minus 9 over 8 RT times V. Okay, so we can continue to break this down. So we've got P is equal to, let's bring, yeah, so this V out of 3 can go out over, so that would yield us RT over V times, let's see, minus 1 would be 3 over 2 minus 9 over 8, which can, going further, P is equal to RT over V times 3/8, as this would give us. And you can set this actually equal, this whole thing equal to 3/8 is equal to P times V over RT, because this is the compressibility factor. We can now use this in order to solve for any compounds given their critical pressure and critical temperature values without needing to solve for other things such as volume. In order to do that, in order to gain numerical values, you'll need to input the critical temperature and critical pressure values for A and B. So we're going to break those down one final time. For B, that'll be equal, B is currently 3/8 times, let's see, RT over P. And we can divide that whole thing by 3 and find B is now equal to RT over 8 times P. So now with this value, as long as you have this critical temperature and critical pressure value, you can input that in order to solve for B. And same thing goes for A. We have A is equal to 9 over 8 times RT times 3/8 times RT over P. And that'll break down, that would be A is equal to 27 over 64 times RT over P. And then once again, these are our critical temperature and critical pressure. And this can be used for any compound in order to solve for these van der Waals equations.